For those of you listening at home, thank you. Jonah just saved my bacon. And your video. Click like and subscribe. Working on worksheet 5E-4, the worksheet that would not die. So, grab your calculators as well, you will need them.
Wait, are we going over this, or did you say it's good?
Kinda, sorta. It's 5E-4 in its entirety is good.
No, it's my calculator.
So if you have it all done, congratulations, you have no more work to do. All right. Let me try.
So we'll have nothing else.
Correct. There is no additional homework until Monday, in which case, no problem. All right. I would like to take a look at problem number 4. This will be our demo problem. I can assist with some other ones. This is the, let me see. This will do it. VFT. Okay, I have your worksheets out. It might help to have your notebooks out in case I drop some hints as to a few things. And calculators out. -4t cubed. Plus 32. Alright. So start from the beginning. They gave us v of t. And they guarantee us that the velocity function is for t greater than or equal to 0. Now, that kind of makes sense. We're not going back in time. So the very beginning of the experiment is when t is 0. They start running the experiment. And there's a particle moving back and forth on the x-axis on number line. For each problem, I said find the acceleration function. So here's what they want us to do. Question 1, find a of t. Question 2, the times when the particle changes directions. Third, the intervals of time where the particle is moving left and then moving right. And then interval moving right. Okay. The times t when the acceleration is 0. And then the intervals of time when the particle is slowing down and speeding up. Get this sort of wound to the board here. My main hint for most of this worksheet is refresh your memory on plus-minus notation. There are 3 possible functions you can use plus-minus notation on. If you use plus-minus notation on s of t, the position function, that will tell you when the particle is to the left, on 0, or to the right. Does that make sense? If it's a plus, that means the position is plus, positive, is to the right of 0, and so on. What does it tell you if you use plus-minus notation on v of t? Michael, take this one. What could it possibly tell you? You remember plus-minus notation where you have positive, negative zones and such? What would that tell you? Because it tells you something different if you do plus minus notation on a VFT.
Slow and fast,
Yeah, kinda, sorta.
or it stops.
That's a possibility. Give me an example. If VFT is positive, what does that mean?
It's going to the right.
To the right, correct. So it's either, it's when it's moving to the right. What else? It's moving to the right, but it's positive. I should have filled these in. Well, this is kind of self-explanatory. Yeah. When it's moving to the right, the velocity is positive. What else could it tell you?
It's moving to the left.
When it's moving to the left, if it's what?
Negative.
If the velocity is negative, and one other thing.
It's stopping and going.
Yeah, in other words, kind of, sort of, when the particle stops.
Oh,
When does that happen?
0.
When the velocity is 0. Correct. So if you did plus minus notation on velocity, all the places that are marked as roots, like x-intercepts with a solid dot, that's where the velocity is 0. And that'll come in handy. What happens if you do plus minus notation on the acceleration? What does that tell you? Pretend that the acceleration is positive. Julius, your son. What would that mean? If the acceleration is positive, what's happening? Kind of. You're so close. What's happening as over time, what's the particle going to do? If the acceleration is positive, in other words, if the velocity is 10, and then 10, and then 10, and then 10, and then 10, what's the acceleration? 0. What if the acceleration is positive? What's going to happen? You're so close. In other words, watch this. 10, 10, 10, 15, 15, 15, 15. What's the acceleration right now? When the 15, 15, 15, 15, 15? It's still 0. So you're very, very, very close. It's the fact something could be going faster and just have gotten a kick, but it doesn't necessarily change the acceleration for the rest of it. There's a word for it. If it's going faster and faster and faster, how do you say that in plain English?
Speeding up.
It's speeding up. Right. That's kind of what's like. So it's when the particle speeds up. And the reason I was being fussy about this is the worksheet was using those words. When the particle speeds up, I'm going to actually qualify this. When it speeds up, I wish it were as simple as saying, if the acceleration is positive, it's speeding up. If the acceleration is negative, it's slowing down. That's not always true. Watch this. You remember that acceleration is kind of like gravitational pull? It's trying to pull you in one way or another, and it's trying to make you go faster and faster in that direction. Let's just say this is just sitting, like it's just bobbing in the water. All of a sudden, acceleration that way. What's going to happen?
It'll go left.
It'll go left. And as time goes on, what should happen? If the acceleration is from that way, and the acceleration stays that way, is it just going to go? What? So let's just say attach a rubber band. In the first second or so, it'll start drifting. How about the second and third and fourth and fifth second? Why? When there's acceleration, what's this thing going to do? Sort of by definition, it's going to what?
Speed up.
It's going to speed up. It's going to start going faster and faster and faster, unless something stops it. Now, if it's going to the left, is the velocity positive or negative, Max?
Negative.
Correct. If you're moving to the right, what's the acceleration? What's the velocity? Positive. Now pretend you're already moving to the left. acceleration starts pulling from the right. That's called a positive acceleration, if it tries to pull you to the right. Does that make sense? Acceleration doesn't care whether you're speeding up or slowing down, really. It cares which way you're going, which way you're going to be speeding up or slowing down. So in other words, if you have an acceleration that's positive, the door is trying to pull me out. That door. I forgot there's another door there. The metal door is trying to pull me out. If there's acceleration negative, the wooden door is trying to pull me out. It's possible you can have two accelerations at the same time, in which case I'd be in pain, but you know, it's one of them is gonna win or I'm gonna rip it in half. But let's just say there's an acceleration of -10 on me. Let's just say, you know, Sister Mary Daniel is dragging me over. And then Father Ron is trying to drag me this way and he has an acceleration. So there's an acceleration of -10 from Sister Mary Daniel, an acceleration of +20 from Father Ron. Who's gonna win? Father Ron. In other words, what am I gonna be doing, physically speaking? Where am I gonna move? That way. And what's gonna happen to my velocity over time? Pulling with -10 and +20, the overall effect is +10 that way. What's gonna happen to my speed? Is it just gonna drift constantly? Mike? What does acceleration do by definition?
Speed up.
It speeds things up. So if I have an acceleration that's not 0, it's going to go faster, 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 until something stops. Does that make sense? So the reason I'm making a fuss about this, oops, when a particle speeds up, it depends on which way it was going in the first place. If I'm headed this way at 30 miles per hour, and there's an acceleration behind me, what's it going to do to my speed? No.
Doesn't make your speed slow down.
Slow down. What if I'm heading this way at 30 miles per hour and I have acceleration that way?
So it'll make it go even faster.
It's going to speed me up. So it makes a complete difference of which way I'm going. When they're asking about what intervals is it slowing down and speeding up, it depends. Which way was it going in the first? In other words, you have to answer this one first. You have to know, is the particle already going to the left? And then if it's pulling to the left, it'll speed it up more. If your particle is going to the left and you have a rightward acceleration, it's going to slow you down. Does that make sense? So when the particle speeds up, it depends on direction. And when the particle slows down, depends on direction. Okay, let's do this. The very first question is find A of t. So, Polly, help me out with that.
Did you put double derivatives
Of what?
S of t?
Yes. Do we have S of t? No. What do we have?
Yeah, you can just do the derivative.
Right. The first derivative of this. What do you got?
-12
Mhm.
t squared
Good.
and plus 60t.
Nice. There's your first question. Clear, gentlemen? We can hold that conversation until later, yes? When does the direction change? Think about which of these would tell you that. Does S of t tell you when the direction changes? Does V of t? Does A of t? Brainstorm and tell me. Give me just throw out an idea. No death penalty if you're wrong. How would you tell when something switched directions? What gives it away? There are several possible answers to that. Give me one.
Well, maybe if you graphed it, you saw when it passes 0.
Yeah, when you graph it, when you graph what?
One of the functions.
Which function?
You would graph the position function.
The position function. If you graph the position function, you'd have up, down, up, down, up. It would tell you like where it is, yeah. And then you could see physically when the direction changes. Now, part of the problem is this is being graphed on a number line. So you'd actually have to have kind of a movie or a video in order to see it go back and forth. Zing, 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 zing. And then you could see, like if you had a timer going on the bottom, and you say, okay, 1 second, 2 second, 3 second, 4 second, 5 second, whoa, it seemed to switch at t equals 4. But what mathematically can tell you when the direction changes? Let me say, for example, if I tell you, let's look at S of t. That tells you the position. Does the position of the particle tell you if it changed direction? If I say, hey, the particle is at 5 spaces to the right, does that tell you if it changes direction there or not? Tells you. No, it doesn't tell you anything about that. It just says that's where it is right now. It could be going further to the right, it could be going further to the left, it could be changing direction. Don't know. V of t, could that tell you when it changes direction? Jack?
Yeah, because
How
if
so?
you see the velocity is negative, you know it's going to the left.
Yep.
And if it switches back and it's going positive.
Right. And guess what has to happen as it switches from negative to positive? What number does it have to pass? 0. When the velocity is 0, there is a good chance there may be a direction switch here. It's not guaranteed. You remember something called a saddle point? Or something, it's a triple root. It like flattens out, which is basically velocity. Think of slope as the velocity. You know this, like kind of like a cubic when you do this. Like here, the slope is positive, slope is positive, slope is positive. What happens here? What's the slope? 0. But then it starts going positive, positive, positive again. It just sort of stopped to catch its breath and then kept going forward. It didn't change direction. So the fact that you have a slope of 0 or a first derivative of 0 might mean it changed direction, but we're not 100% sure. That's actually what plus minus notation is very good for. If you can see a zone that's positive and a zone that's negative, dead giveaway. It changed direction. Does that make sense? So when it switches from positive to negative, basically when V of t is from positive to negative, or from negative, I was using arrows to positive, that's the dead giveaway. That'll tell us when the direction changes. And plus minus notation is very good for that. Let's see if we can find that. So tell me what to do. I'll do it down here. How would we find the direction changes? Max, take over. And say, here is a test question. Find where the direction changes on this thing. Where would you start?
Could you set it to 0?
So what equal to 0?
V of t.
You could. Let's try it. There might be, remember, it's not guaranteed, but it's useful. So what is V of t? You read it off from?
Negative 4t cubed plus 30t squared.
Okay. Equals
0.
0. Solve.
30t squared plus 4t cubed.
I wouldn't do that. There's a reason why not. That's solving with algebra.
Oh.
Why wouldn't you solve with algebra? When you're adding, subtracting, multiplying, and dividing and square rooting on both sides, that's called doing it with basic algebra. And that doesn't work in this problem. Why not? Go.
Multiple different species of x.
There's different species of the variable. If there are 2 different powers of x, it won't solve. Because if you want to get this on this side, you might try and square root this side and it'll disaster this. Or you could cube root this and it'll disaster this. So you're going to be stuck in a corner. How can you
Wait,
solve?
you can't like.
We can't, like if you move this to the other side and then try dividing both sides by t squared or something like that?
You can't do that.
Correct, for 2 reasons. Number 1, it's algebra. And number 2, dividing by t or t squared or t cubed is very dangerous if t is equal to what? 0. And it very well might be. So in other words, it might blow the whole thing sky high.
Do factor t out.
Ah. What's the GCF?
T squared.
And you can probably pull one more thing out.
2t
2, and the first term's negative, so
Negative two.
negative 2t squared. Tell me what's behind, left behind.
2t plus 15,
2t plus, close,
negative.
negative 15 equals 0. Solve.
Okay, so negative 2t squared equals 0.
Yep.
So then it's just t is 0.
Yes, by the way, it's very good we didn't divide by t, because we would have died. And then here?
And then 2t equals 15.
Yep.
So t equals 15 over 2.
Ah. So right now we have two time values where the velocity is 0. At t equals 0 at the very beginning of the experiment, and at t equals like 7.5. So either of these might be a case. Now, the fact that this is right at the beginning of the experiment, it'd be hard to tell if it was a sign switch, if it was a direction switch, because we don't know what it was doing before the experiment started. So there's no way to test it. This is the only possible candidate for a sign switch. How would we know for sure? How do we know it's not one of these, it slowed down, stopped, and then kept going in the same direction? How would you tell? No, take over.
Well, you could plug some values in, like before it and after it to see.
What does that sound like?
Plus minus notation.
It's plus minus notation. Correct. Let me see. Does everybody have this step here? The SFT, blah, 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 blah. Okay, I need some space. All right. And if you get totally stuck on it, you can just watch the video. So let me get this out of here. We're talking about plus minus notation. Jenna, do plus minus notation on what? Which of the three formulas?
The second V of t.
V of t, correct. So I'm going to do plus minus notation on V of t. Whoops. And again, V of t looks like this after you've factored it. Negative 2t squared, parentheses, 2t, I'll do minus 15 just for all time's sake. Okay? So tell me how to do plus minus notation again. Step me through this. Julie Sisha, how do you start plus minus notation? What do you do it on? Like, what do you draw it on? Number line. And what sort of things do you mark on the number line?
You have 0 and 15.
Okay, what are those? Those are what? Those are roots, correct. I mean, they're not roots of the original function, but yeah. Roots of the velocity function. What other things could we theoretically graph on a plus minus notation? Like, what sort of things do you put on plus minus notation for markers? Vertical asymptotes, correct. There's one other type, well, two other types of what we've never actually done before with them. Holes. Are there any vertical asymptotes, Michael, in the velocity function?
Oh, no,
No. How do you know so fast?
because there's nothing on top.
Right. There are no T's on the bottom. Are there any holes, Jack?
No,
Why not?
because there's nothing on the bottom.
Right. You have to have something on the top and bottom, and holes don't work. So don't worry about vertical asymptotes or holes. The two roots are t equals 0 and t equals 15 halves. Questions? Polly, take this one. T equals 0. What kind of a root is that? Here's where we got them in the original. There's a special, this is t squared, and this is regular t, if that's a hint. Single, double, triple, quadruple,
Oh, it's single, right?
for t equals 0. So what we're doing is setting these equal to 0. Technically, we could have done this, negative 2t times t times 2t minus 15. What root would this give you?
It's a double root.
It's a double root, because there's two roots at 0. What kind of a root at 15 over 2?
Single.
That's single. Does that make a difference on plus minus notation? Yeah. What happens with a double root, Max?
Doesn't switch.
Correct. The sign does not switch on plus minus notation for double roots. How about single roots?
Switches.
They do switch. So there are only two things to mark, 0 2, which is 7.5. There's a double root at 0 and a single root here. So we've got 3 regions, region A, B, C. Somebody help me out in testing, if you'd be so kind. Jack, take this one.
Let's do,
I'd love to do 0, but I can't. It's
let's
one
do
of them.
1.
1. Which region is that?
B.
Region B. So I'm gonna mark this as x equals 1. So B is equal to what? I see, I'll just do this version.
So you
It's,
got negative.
It's negative something, and then I'll do the t squared, and then I'll do the parentheses. So it's negative, what about t
Oh.
squared if its x is 1?
Then it's positive.
Positive, and then,
Another negative.
yeah, plug in a 1, and this is 2 minus 15. By the way, you could have just done the negative in the first place, yeah. What's your result?
You got a positive.
Positive. B is a positive region. What about C, John?
That means it's negative.
Negative, and how about A?
Positive.
It's also positive, because double root doesn't change. Somebody interpret this for me. We're looking at the velocity formula. And we've got 3 regions. Michael, what does this read? Region A is, the particle's doing what? It's going to the right. It has a positive velocity. How about region B? To the right. How about C? To the left. Did it ever change direction?
Yep.
Where?
Oh, 15/2.
At 15/2. Where does the direction change? At t equals 15/2. Did it change direction at t equals 0?
Yep.
No, it was one of those triple root points. It just slowed down, stopped, and then kept going. So if anybody had been starting to measure like an hour before, like some overachiever came into the lab and said, I'm gonna start an hour early, clickety click, click, click. And they watched this before we started, they would have seen it to the right, to the right, to the right, stop, and then start it to the right again. Does that make sense? Plus minus notation was one of the only ways that would be obvious. Next problem. Intervals when it's moving left and intervals when it's moving right. Yeah, go ahead.
So like, what about before that person who came in early?
Oh, what
Like-
happened
like-
before
like-
this?
Like, it
Actually,
doesn't
you tell
have
me.
to have a starting point?
Interestingly enough, how far does this go?
Oh, infinity.
Forever. That means if you went 5,000 years into the past, and somebody invented a time travel machine, went 5,000 years in the past, and I'm gonna watch this thing for 5,000 years. This thing's gonna be moving to the right, to the right, to the right, to the right for 5,000 years.
Sure.
Yeah, exactly. And then it'll stop, and then move to the right for 7.5 more seconds, and then it'll move to the left forever. Make sense? While we're at it, can we get intervals for when it's moving to the left and to the right? We should have the data in front of us now for that. Julia Seashine, help me out with that. In interval notation, so t belongs to what? When is it moving to the left? 15/2 to, if you're going to the right, it's, the fact that this is a negative region doesn't mean it's negative infinity. Yeah, it's a positive infinity. Do you include 15/2? This is a tempting question. Look up here. Everybody tune in on this. Should I include 15/2 as part of my solution for when the thing's moving to the left? You're shaking your head? No, why not?
Because it's at 0.
It's staying still there, just for an instant. That's one of the 2 places where it stopped. Yeah, it's so tempting because it's a solid dot. It's like, come on, I want it. But the interval is moving left. That means the velocity is less than 0, not less than or equal to 0. So it's round bracket, round bracket. Can somebody give me intervals for going to the right, if any exist? Jack? T belongs to the left.
Can you just go all the way through, so t belongs?
Good question, you tell me.
Yeah, because the number stops.
Are you sure?
Well, I guess, yeah, it has to stop at 0.
It does stop
So
at 0.
you have to do it 2 separately.
Right. Now, I think I see what you're saying though. Give me 2 intervals and then I'm gonna change the answer a little bit. What's the
Okay.
first interval that seems obvious?
Negative
From negative
infinity
infinity.
to 0.
To 0, round, square,
Both round.
both round, okay, and then union, what?
0.
Okay.
to 15/2, both
Okay.
around.
Correct. Now, there's one thing that they told us at the very beginning of the worksheet that will modify that answer. Can we see it?
That t has to be greater than or equal to 0.
Right. We're not worried about the person who went into the past and started early. We're worried about the experiment that we're running. So what do we have to throw away?
The negative infinity,
To what?
0.
To 0. It was a perfectly good solution. They just didn't want it. They said, hey, I showed up here at 6 a.m. and started running this thing for 4 hours. That's really nice. Useless. That's rude. So it's good practice. It builds character. So the only thing we have is from 0 to 15/2, round bracket, round bracket. Make sense? Now, when is the acceleration equal to 0? Max, take this one. How do you do that?
Well, you have AFT,
We have AFT.
so could you set that to 0?
Exactly. It's just straightforward. Negative 12 t squared plus 60t equals 0. Solve for it.
Okay, so you pull out a negative 12,
Correct.
and then you
There's
get
something else.
t,
T, and then what's left behind?
and you have t plus 5.
Pull that in negative 5. Minus 5, correct. Can you solve it in your head?
So t equals
0, and t equals
5.
5. Correct. So when is the acceleration is equal to 0? Should I count t equals 0? According to the time values that they want. Josephine. Take a wild guess. No death penalty if you're wrong. You'd seem to me no. However, they want to include 0. Isn't that annoying? I admit, that's totally annoying. Would I care if it's accelerating 0 at the beginning? Maybe, depends on my mood. But they want it. So they're our bosses, so they're paying our paycheck, so, all right, here are the two values they want. Normally I would throw that away because I'm like, we're just starting, of course it's 0. I mean, nobody just whipped it and then, say, okay, already in motion, let's start the experiment. It's a little weird, but I want to include both of these. So what happens is, by the way, can I look at this velocity chart? When, and by the way, this is 7.5 seconds. At 0, is it being pulled left or right? Michael. At t equals 0, is the particle being pulled to the left or pulled to the right?
Right.
Why do you say that?
Wait, maybe none.
What's that?
Well, none. Stop.
None? Okay, why do you say that?
Because
You're right, by the way.
when you put a t 0, you get t is 0, so there's no acceleration.
Right. At the very, very beginning, there is no pull left or right. Pull is acceleration. There's no pull when t is 0, and there's no pull when t is 5. What's happening between 0 and 5? Which way is it being pulled? You could deduce it just by looking at the velocity. From 0 to, like here's 5 seconds. Is it moving left or moving right? No.
Right.
Moving to the right. So guess where the first acceleration probably shows up from?
From the right.
From the right. Does that make sense? Logical sense? There's one way to prove it. Do plus minus notation on the acceleration. Polly did this one for me. What do we mark on the acceleration plus minus?
0 and 5.
Yeah, those are the only ones we have. Are those roots, vertical asymptotes, holes?
Those are roots.
Those are roots. So solid dots. Single roots, correct. So we've got region A, B, C, and they're single roots. How do you run that? Go ahead and finish it up.
We can plug in 1.
Sure. X equals 1, that's region B. So A is equal to what? I just say these two things. So something times something. Plug in a 1 here,
It's going to be negative.
negative, and plug in a 1 here,
Negative.
negative. What does that make?
So positive.
Yes. That's what we suspected. there's a positive acceleration. When does the positive acceleration stop? Jack?
Wait, sorry, I'm catching
Okay.
up.
When does the positive acceleration stop? In other words, it started, there was a pull from the right at 5 seconds, correct?
And then it's kind of catching up until 7.5. That would.
Yeah, it's sort of like, well, sort of a coasting to a stop, if you will. Yeah, it's sort of like pull, 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 sorry, let go. And it drifts to a stop. It's not gonna stop instantly, but it's gonna drift, drift, drift. Hey, nobody's pulling me anymore. It's kinda like somebody pulling you on a sled. It's kinda like, oh, this is totally mean, don't do this. And they're like, here's your younger brother or sister. Lolly, lolly, la, we're going to the, oops, I just dropped you, bye. Now, they're not gonna stop instantly, and by the way, don't do that to me. But they will keep moving for a little while and then stop. Make sense? Here, it kept moving for a little while and then the velocity stopped. What happened to the velocity after that? It went to the left. What's the only thing that could cause that? Your little brother or sister start moving backwards. What could possibly cause that, Michael? Like I'm pulling my little brother or sister, and then oops, I drop, hopefully by accident, because I like to be a morally upright person. That would be stupid, but it would at least be morally, non-corrupt. But think of the sled on, like being on Teflon, like super duper slippery, and assume that I can actually walk on Teflon, which is super unrealistic. But let's just say, if there's no friction, that thing is gonna keep going. It's not gonna drift to a halt. Friction causes that. Something else caused this to stop and then go backward. What's the only thing that could? What sort of thing? I'm pulling little Mortimer on the sled. I drop little Mortimer because I'm either stupid or careless or I have leprosy on my right hand. I can't tell, I can't feel anything. And then I keep walking, and then Mortimer's just drifting forward at the last speed that I left him, which heaven only knows what it was. But then something happens. Mortimer and sled slow down, stop, and then start moving backwards. What could cause that in general? Michael? Yeah, you're on the right track. Gravity pulls down, though. What could cause Mortimer to start moving backwards? Acceleration in what direction? What does that mean? To what direction? To the left, correct. Something is pulling Mortimer backwards. It could be a black hole that just appeared over in Mrs. McGillicuddy's house across the street, but something is pulling Mortimer backward with a negative acceleration, that way. The only thing that can stop a frictionless thing from moving forward is if something pulls it backward, or if it hits something, which is an acceleration, it just hurts. Questions? So question, describe what happens, let's not chit chat, please. Describe what happened from the get-go. There is a particle, a sled if you will, at t equals 0, what is it doing at that very instant? John? At t equals 0, what's happening? Describe the position, velocity, and acceleration. What's happening? What's the position? That's an interesting question, by the way. Do we know?
0? Oh, no, we haven't.
We do not know the
found that yet.
position, because we don't have the formula yet. What's the velocity there? At t equals 0.
0.
0. It's not moving. What's the acceleration at that instant?
0.
0. Now, move forward a little bit in time. Max, take over. What happens now?
So it slows down when you get to 0.
We're past that.
And then go fast.
You want me to repeat the question?
Yeah.
Okay.
Sorry.
Now, we're starting at t equals 0. At that very instant, we don't know the position because we don't know the formula yet. The velocity is 0, the acceleration is 0. If the acceleration is 0, would you expect it to start moving? No. But as you get like 1/2 second into the experiment, what's the acceleration? Positive, negative, or 0? Positive. what's that gonna start doing to your particle?
It's gonna accelerate. Well, it's
In what
going
direction?
Faster to the right.
It's gonna start moving to the right, and it's gonna start speeding up. Correct. It's going at 0 miles per hour right now, and then there's a pull to the right. So it's gonna start moving to the right, it's gonna start it's gonna start accelerating to the right. Until when? What's the first interesting event that happens? So it's it's being pulled to the right and it's moving to the right. So it has a velocity that's positive. What's the first interesting change that happens? No.
One at t equals 5,
What happens then?
the acceleration goes to 0,
Right, the acceleration stops to the right.
so it's no longer speeding up.
Correct, it's no longer speeding, it's still moving, and it's still moving at a constant speed, but it's not speeding up anymore. A little bit after 5 seconds, what happens? John,
It's also
why? You're right. Which way is it still moving?
to the right.
Still moving to the right, but it's slowing down, why? What's causing that?
Acceleration.
In what direction? Yes, an acceleration to the left just showed up. By the way, single root, single root. This is the chart for the acceleration. After 5 seconds, you're getting a negative pull. You're getting a pull backward. By the way, there was a pull backward before, which is kind of interesting. So before, if somebody had arrived, hours early, they would have had a very strong force being pulled to the left until t equals 0. So when I walk into the door, it stops pulling, and then starts pulling to the right. And then at 5 seconds, it gives up and starts pulling to the left again. So at 5 seconds, the acceleration changes from right to left, from positive to negative. What's the next interesting event that happens? Jack?
That 5 seconds starts pulling, wait,
We got the 5 seconds, that's when the acceleration changes from to the rightwards to leftward.
yeah,
What after the 5 second mark, what's the next interesting event that happens?
when it hits, 7.5,
What happens then?
well, the velocity changes
True.
to negative
And at that instant, the velocity is what?
0.
0. So in other words, it comes to a halt, stops for an instant, and then starts doing what?
Going left again?
Starts moving backward.
Oh,
Did everybody see that? Now, where are the positions on this? No clue. Did they ask us for the positions? Look in the instructions. Did they ever ask us for the position function? No. There's a reason for that. We don't have enough info. If they had told us, by the way, the position was 10 when the time was 0, we could have done an antiderivative here, found the c, and done that. They just left it alone. Somebody tell me, we should be able, we've got the acceleration, this is when t is 0, and t is equal to 5. Slowing down, you tell me. Here's the acceleration chart. At t equals 0, is it slowing down? Julie Sishan. No, it's sitting still, and it's about to start doing what? Speeding up. In which direction? To the right. It's going to speed up, speed up, speed up to the right. What happens when t is equal to 5? Michael? Why?
Because the C range is negative.
Correct. It starts slowing down because it's moving to the right. Look at the velocity. Like this is from 0 to 7.5, it's moving to the left. What the heck? My left, you're right. Let's point this way. From 0 to 7.5 seconds, the thing's moving to the right. During which interval was it accelerating to the right, Max?
from 0 to 15 over 2.
It wasn't accelerating that whole time.
Wait,
Look at
I
this.
thought you said-
This is the velocity chart. This is the acceleration chart.
well, 0 to 5.
From 0 to 5. Does everybody see that something is going to be different from 5 seconds to 7.5 seconds? What's it doing from 5 to 7.5? Josie? Slowing down. We just found our first interval. From 5 to 7.5. t belongs to 5 to 7 point, I'll even do a decimal for you. Round bracket, because it doesn't include the time when it's actually just floating at 0. Is it slowing down any other time? Basically, when the acceleration changes from positive to negative or negative to positive, that's when it'll slow it down. Is that gonna make sense? If you're going forward and then you switch acceleration, it's gonna start dragging you, it's gonna slow you down. And there's nothing pulling you forward anymore. So only when you have a sign switch could it possibly be slowing down.
Does that mean that it's slowing down between negative infinity and 0?
Yes. Now, that would be interesting, but they didn't want us to consider it. So
Okay.
it's out of our interest range. So yeah, there is some slowdown thing here, but, because it had to be, because if they're pulling negative, something happened in order for it to, because at 0 it wasn't even moving. But they don't even care about that. There's only one slowing down interval. When is it speeding up? Give me an interval where you know the thing is speeding up. Do this here. Exactly, from 0 to 5. It started at, it's just velocity of 0, and then it starts moving to the right faster and faster. So it's got to go from 0 to 5. Is there anywhere else where it starts speeding up? In the interval where we care, so don't worry about the negatives. No.
It's also speeding up from 7.5 to infinity.
Correct. So union from 7.5 to infinity, because it's accelerating backward to the left. Does that make sense? Are we getting this? This does take a while to finish problems like this. I will probably even give you a little bit of time on Monday to finish this off and bring any last questions, because this is one of the more involved assignments of the year. Once you wrap your brain around what the physical world and the math do when they talk to each other, that's 80% of the battle. If you just stare at this thing saying, what the heck is going on? And if you can picture it, if you were to say, okay, from 0 to 5, the thing is accelerating to the left and it's moving to the left. And then at 5 seconds, it starts slowing down, it's still moving left, until 7.5 seconds, then it stops, then it starts accelerating backward and starts moving backward forever. That's what I want you to know. Clear? It's complicated first 100 times you do it, and then it gets a little easier. I'm not sure if it'll ever be easy.
Wednesday, Mr. Conklin.
What's that?
This is Denver Riverside, and she gave us this. And we were like, is it due tomorrow? And she said, well.
Oh, you did it all already?
He didn't say, so I think it's due Thursday. So I tried to do it all. It was terrible.
That's okay.
It was so bad.
On behalf of the world and me, I apologize. So, is this making a little more sense? I mean, it's complicated, it's involved, it's detail-oriented, but if you can at least comprehend what these pieces mean. If you know how to factor, you know how to do plus-minus notation. If you know how to do derivatives and antiderivatives, you should be in fair shape. Any last questions? Because I gotta get you out of here. Please stand.
I have one question though.
Yeah, question.
For number 1, the acceleration function is just -2.
Correct.
And so,
That means it's accelerating forever and ever, amen, 2 to the left. That means even if it starts moving to the right, it's doomed. It's doomed to go left,
okay.
eventually.
So some ways it's even simpler.
I'm sorry. Okay. Let us pray.
Bye, guys.
Bye-bye, y'all.